Hello, my name is Shreya Upasni and today I'll be presenting my thesis project. The topic here is enhancing the robustness of AI-based malware detection, a hybrid approach combining static and dynamic analysis to defend against adversarial invasion attacks. In this project, I have designed and tested malware detection framework that combines static and dynamic features to improve both detection accuracy and resistance to adversarial attacks. Malware detection is a critical defense for keeping our systems safe from constantly evolving cyber threats. There are two main approaches we usually see: static analysis, which examines the structure and code of a file without actually running it, and dynamic analysis, which observes the behavior of the program in a controlled environment while it executes. However, each method alone has weaknesses. Attackers can design a malware to evade one or the other. To make things more challenging, adversarial attacks can subtly modify malware so that it slips past detection while still performing its malicious actions. The aim of my research was to see if combining static and dynamic features would improve malware detection performance and make systems more robust against adversarial attacks. For this, I used two datasets: AMBER 2018 for static features and CIC Malmem 2022 for dynamic features. I evaluated three configurations: static only, dynamic only, and a hybrid one. Then I simulated adversarial attacks and measured how much performance has been dropped. Finally, I identified which model setup was most robust overall. When reviewing existing studies, I found that very few have treated hybrid analysis combining static and dynamic features as a unified detection framework. Moreover, the robustness of such hybrid setups against adversarial attacks is still largely underexplored. Finally, there has been no thorough comparative evaluation of hybrid feature fusion against a wide range of attack strategies, leaving a clear research gap that my work aims to address. I began by pre-processing the data, that is, cleaning, scaling, and balancing it. Static features came from AMBER 2018, while dynamic came from CIC Malmem 2022. With synthetic benign samples added when needed, I trained logistic regression, random forest, XGBoost, and MLP on static, dynamic, and hybrid datasets. Then evaluated them using standard metrics and tested robustness with targeted perturbations and FGSM attacks. For the static model, I used AMBER 2018 features, which included file structure statistics, byte histograms, and import tables. Among the algorithms tested, Random Forest performed the best, achieving high true positive rate while keeping false positive low. However, one key limitation was that these models remained vulnerable to invasion techniques, particularly obfuscation and deliberate feature manipulation, which could bypass detection without altering the malicious intent of the code. For dynamic model, I used behavioral features from CIC Malmem 2022, which included API call patterns, memory usage, and overall system activity. Since the dataset lacked enough benign samples, I generated synthetic benign data to balance it, ensuring fair training. These models achieved very high accuracy during the normal testing. However, when exposed to adversarial attacks, their performance dropped sharply. This showed that while dynamic analysis can be powerful, it is also highly sensitive to feature manipulation that disguises malicious behavior. The hybrid model combined both static and dynamic features, with each sample containing information from both domains and paired by class. Among all models tested, random feature once again performed the best, showing strong resilience under FGSM adversarial attacks. By merging structural indicators like file statistics with behavioral indicators such as API calls and memory activity, the hybrid approach improved detection accuracy and made it significantly harder for adversarial manipulation to bypass the system. There were two types of adversarial attacks tested: targeted feature changes, Guided by importance ranking and FGSM generated adversarial samples. Under FGSM, the MLP model showed noticeable performance drop. In contrast, the hybrid random forest maintained accuracy with only minimal loss, proving it to be the most robust configuration against such manipulations. There are several limitations to this study. Firstly, it relied entirely on pre-extracted datasets, which may not fully represent current threats. Secondly, the CIC MelMem 2022 dataset did not contain genuine benign samples, so synthetic ones had to be generated. This may not perfectly mimic real benign behavior. Other point is that the static and dynamic features came from different binaries, meaning natural correlation between them were absent. Also, no live sandboxing was performed and no live malware was executed, which limited the scope to an offline dataset driven analysis rather than a real time operational environment. Building on the limitations discussed, there are several promising directions for future work. Firstly, I would focus on live data collection where both static and dynamic features come from exact same malware and benign samples, ensuring natural correlations. At the binary level, adversarial malware generation could be implemented to simulate real world invasion tactics. On the modeling side, advanced deep learning such as CNNs and transformers could be explored to capture more complex patterns. Adversarial training would be applied to improve robustness against such attacks. Finally, moving beyond the offline experiments, real world deployment and scalability testing could be performed, incorporating sandboxing and controlled execution of the live malware to fully evaluate performance in operational environments. In conclusion, this study demonstrated that hybrid feature fusion, combining both static and dynamic indicators, consistently outperformed single domain models in terms of robustness. Among the tested approaches, the random forest in the hybrid configuration proved most resilient under simulated adversarial attacks. These findings strongly support that the adoption of hybrid systems for practical and real world malware detection, where both detection and robustness are critical. Here we have my static model. I began by sampling data from AMBER 2018 dataset, which contains pre-extracted static features from executable files. I selected an equal number of benign and malware samples, flattened them, and prepared them for the training. I split the dataset into training and testing sets. Then I trained three classifiers: random forest, logistic regression, and XGBoost. The ROC curve on the screen shows that random forest and XGBoost performed almost identical with an AUC of 0.99%, indicating very strong classification ability. Logistic regression, however, performed poorly with an AUC of just 0.44, meaning it struggled to separate benign from malicious samples. In terms of accuracy, both random forest and XGBoost reached 92.5%, while logistic regression only reached 45%. This performance gap is also reflected in confusion matrices. While random forest and XGBoost correctly identified most samples, logistic regression had significant misclassifications. Finally, I ran simple adversarial attack by modifying one important feature in malware sample to match the benign mean. Even after the attack, random forest and XGBoost maintained their accuracy, showing robustness, while logistic regression's accuracy remained low. This confirms that in the static setup, methods like random forest and gradient boosting are far more resilient to such perturbations. This is the dynamic model of my project. I started by loading behavioral feature profiles from CIC MelMem 2022 dataset. Since the dataset only has malware traces, I created synthetic benign samples by generating random values within the range of malware features. This allows me to have balanced dataset for training. Once I combined benign and malware data, I split it into train and test sets, then train three models: random forest, logistic regression, and XGBoost. The ROC curve here shows the test performance. Random forest and XGBoost are perfect or near perfect with AUC close to 1.0, and logistic regression is slightly lower at 0.95. Then I simulate two adversarial attacks. Attack 1 modifies a single important feature in malware samples to match the benign mean. In this case, none of the models performance dropped significantly, meaning they are not fooled easily by this simple change. Attack 2 targets the top most 5 important features for random forest, replacing malware values with benign range values. Here, XGBoost collapses to 47.5 accuracy, showing high vulnerability, while random forest and logistic regression drop slightly but still remain useful. So, this part demonstrates how dynamic feature based models can start with very high accuracy but may have varying robustness when multiple critical features are manipulated. This is hybrid analysis model. It combines both static and dynamic features into one dataset. First, I extracted static features from Ember dataset. These describe the file structure like header statistics, imported library counts, and section entropy. At the same time, I take dynamic features from CIC Malbem dataset. These are behavioral metrics like CPU usage, network connections, and API calls during executions. To make a fair comparison, I sample equal numbers of benign and malware examples for both static and dynamic datasets, align their columns, and then merge them side by side. This produces a richer feature set that captures both files' code level characteristics and its runtime behavior. I then train three models: random forest, logistic regression, and XGBoost. In the clean testing, random forest and XGBoost achieved perfect accuracy, while logistic regression performed slightly lower, that is 0.86. You can see the ROC curve in that random forest and XGB boost hug the top corner, meaning they classify almost every sample correctly. Next, I run advanced adversarial attack. I identify the top 5 most important random forest features and replace malware values with benign values. After this attack, random forest dropped slightly to 95% of accuracy, showing strong robustness. Logistic regression fell to 62.5% and XGBoost dropped to 70%, showing they are more vulnerable to this feature manipulation. Finally, I tested a multi-layer perceptron neutral network for hybrid data. It achieved 90% of accuracy on clean data with balanced precision and recall. Under the gradient-based FGSM adversarial attack, its accuracy actually improved slightly to 95% because the perturbations did not significantly change its decision boundary. This demonstrates that hybrid approach offers excellent baseline accuracy and with a right algorithm can maintain high robustness against adversarial attempts. Thank you.